Hi there. So now what we're going to do is we're going to talk about section 6.3, which involves definite integrals. So before I actually get to that, what I want to do is ask you this question. Suppose I have a graph of a function, and why don't we say that this line is y equals 6x, okay? And suppose I wanted to find the area bounded by this line from x equals 0 to, say, x equals 3. Okay? In other words, I want to find the area of this region, so bounded by this line and the x-axis. Okay? That's something that we can do because it happens to be a triangle. We know that the area of a triangle is 1/2 times the base times the height. So we get 1/2. My base is 3. Now what's my height? Well, my height is my function value at 3, which I think you'll grant me is 18. So if we compute that, we're going to get 27. Okay? Now, I want you to keep that in mind as we proceed through this section. What I'm going to do is explain to you what the fundamental theorem of calculus is, and we're going to apply it. Now, the motivation behind these things with the definite integrals will be further explained when I talk about sections 5.1 and 5.2. There's no homework for those sections, but they are very important for you to watch the video and read the book because that will give you the background scoop of what we're actually doing here when we compute antiderivatives and specifically what we call definite integrals. Okay, so just keep this guy in mind. Okay, so we want to use the fundamental theorem to find definite integrals. So what I'm going to tell you is what the fundamental theorem says. As you can guess, if it's called the fundamental theorem, it's probably pretty important, okay? What this says is the following. If a function f of x is continuous on a closed bounded interval from a to b, then notice I'm computing an antiderivative, but now I'm taking these values a and b, putting them there. If I want to take the antiderivative of my function from one point to another point, that's equal to my antiderivative evaluated at b minus my antiderivative evaluated at a. So I'm saying that this capital F is my antiderivative. In other words, if I took the derivative of this cap F, I would get my function inside. Okay? Now, I claim what we're doing is really no different. What we're when we compute our antiderivative, there's just going to be an added step where we actually have to evaluate this at various values. Okay? Now, one reasonable question to ask is what's the difference between an indefinite integral versus a definite integral? When you're computing an indefinite integral, what you're doing is computing it in general. Notice there's no values here. A definite integral is when you have values here. Okay? Now, you will see momentarily what we're actually computing when we find our definite integrals. So, my first example, I'm going to erase this graph, but I'll keep this area business here, is what if I wanted to compute the definite integral of 6x dx? Notice it's my same function. And now what I want to do is not just compute my general antiderivative, which we know would be what? 6x squared over 2 plus a constant? Well, 2 goes into 6 3 times, so we get 3x squared plus a constant, okay? but we want to compute that from 0 to 3. Okay, where did I get those values 0 to 3? Well, remember, didn't we want to find the area bounded by this function and our x-axis from 0 to 3? Okay, so you might ask, how would you do something like this? I'm going to erase the board here and pretend like we never did that. Okay, so when you're computing a definite integral, you still start the same way. You start by computing the antiderivative, which we know is 6x squared over 2 plus a constant. Now, what the fundamental theorem says is what we do now that we computed our antiderivative is we evaluate that function at our top value and subtract off what we get when we evaluate it at our bottom value. Okay? So the way I show that is I'm going to evaluate that from 0 to 3. So we have f of 3 minus f of 0. Okay? So what I do is I plug 3 in here, so I get 3 times 3 squared plus a constant minus 3 times 0 squared plus a constant. All right, well, 3 times 3 squared, that gives me 27 plus c. Okay, I think you'll grant me that this is 0 plus c. I distribute my negative sign. That just gives me a minus c. And so we got 27. Look familiar? Okay, so I'm foreshadowing where we're heading with these, but what I will tell you is when you compute a definite integral of a function, what you're doing is you're finding the area between that function and the x-axis. Pretty cool, okay? So, again, I'll give you the lowdown soon enough. The other comment that I want to make is when you compute an indefinite integral, you get some function whose derivative is what's inside, and you put plus a constant. Notice here, my constants cancel each other out. So my point here is all you need to do is compute f of b minus f of a, and you don't need to worry about those constants. Okay? So what I would like to do now is work through some examples here. Or I should say some more examples. All right, so what if I want to compute the definite integral from 0 to 2 of 3x squared plus 4x plus 3 dx? Okay? So what my first step here would be is to compute my antiderivative as I always do. Okay? So let's do this term by term. We don't deal with these numbers until the very end. So we get 3x cubed over 3. Next term, you rewrite your constant, take the antiderivative, so we get x squared over 2. And then the antiderivative of 3 is 3x. Okay? So let's just clean this up a little bit. We get x cubed plus 2x squared plus 3x. And I think you'll grant me if you take the derivative of this, we certainly get what we had inside. So now what we do is we evaluate that from 0 to 2. Now whenever you're doing polynomials and you have a 0, it's always, at least in my mind, a pretty exciting thing, just because evaluating at 0 just cancels things out. So f of 2 minus f of 0, so if I plug in 2, I have 2 cubed plus 2 times 2 squared plus 3 times 2 minus, well, I think you'll grant me any place I plug a 0 in here, I just get a 0. Okay, that doesn't always happen, for example, with exponential functions. Okay, so 2 cubed is 8 plus 6. So we get 6, then minus 0. So 16 plus 6 is 22. There we go. Okay, let's do another one. What if I want to compute the antiderivative of, from 1 to 4, of 1 over the square root of x dx? So again, what I do is I start out by first rewriting this so that I can take my antiderivative. So I brought my x upstairs. And now what I do is I take my antiderivative here. Well, if you add 1 to negative 1/2, you get a positive 1/2. So it's x to the 1/2 over 1/2. I think you'll grant me that that's the same as 2 square root x. And we want to evaluate that from 1 to 4. This is pretty sweet. So we evaluate that at 4, and then we'll subtract off what we get when we evaluate it at 1. So if I do this, I'm going to have 2 times the square root of 4 minus 2 times the square root of 1. So 4 minus 2 is 2. All right, let's go through some more examples. What if I have the antiderivative of, how about 2e to the x, and we'll do that from 0 to 1. All right, so we're going to compute the antiderivative. This is always fun. The antiderivative of 2e to the x is 2e to the x. And we want to evaluate that from 0 to 1. So first we'll plug in 1. So don't we have 2e to the first minus 2e to the 0? And what do we get? We get 2e minus 2, since e to the 0 is 1. All right. So now let's do an example like this. What if I, oh, this is fun, from 1 to 2 of, how about 1 over x plus 1 dx. We're going to keep it pretty mellow. Okay? So how would we compute the antiderivative of that? Well, the antiderivative of 1 over x is log x. The antiderivative of 1 is 1x. I evaluate that from 1 to 2. So it's f of 2 minus f of 1. So what do we get when we plug 2 in? We have the natural log of 2. We could put the absolute value, but that's positive, plus 2, minus the natural log of 1 plus 1. All right, well, this doesn't simplify a ton, but it does simplify a bit, because what is the natural log of 1? It's 0. So we just get a 1 here. So we end up with the natural log of 2 plus 2 minus 1. So we'll write that as the natural log of 2 plus 1. If you want to get a decimal approximation, you're more than welcome to do so. All right, so that is essentially what we're going to be playing with in section 6.3. Now, while we're at this, why don't we also then talk about section 6.6? Because what I'm going to be doing now is combining some of our techniques. Okay? So, section 6.6 is the one other technique we're going to learn of computing antiderivatives. Okay, what we're going to talk about is a method called substitution. Now, this method only works in very carefully constructed exercises, okay? It doesn't always work across the board. So, let me put it to you this way, okay? So you're going to think that this kind of looks like magic, like I'm doing a fast one on you here. But it's by the way these problems are written that they just happen to work out so nicely. And essentially we can look at this as kind of an anti-chain rule. So what if I wanted to take the antiderivative of e to the sine theta times cosine of theta d theta? Okay, theta is just a variable just like x is. It's just a very common variable that we use when we're doing our trigonometry. All right, well, given our current knowledge base, we don't know how to do this. So what our goal is when we do integration by substitution is we want to rewrite this integral in a form that we can take the derivative, antiderivative of, okay? So the idea is that we're going to replace this complicated expression with a simpler expression yet equivalent one, okay? Now, one of the things that takes people perhaps the longest is to know, what do you substitute? And you know, there's some hints that I can give you, but a lot of this just comes from practice. In general, the things you tend to substitute are things in your exponents, in parentheses, what's under a radical, and then when all else fails, there are times when you're going to substitute your denominator. Okay? So, for example, with this guy, what we're going to do is we're going to compute the antiderivative using substitution. Okay? So, notice I have an exponent here. I'm going to substitute that exponent. I always use my letter u. That's just out of habit. So what my goal is to rewrite this integral where my variable is u, but it's got to be equivalent to all of this. Okay? So what are our steps? The first step is make your substitution. Okay? My next step here is to take the derivative of both sides. The derivative of u is 1 du. Again, we always have to talk about what we're taking derivatives and antiderivatives with respect to. And what's the derivative of the sine of theta? It's the cosine of theta d theta. Okay? So, what we're going to do now is rewrite this integral, but in terms of u. Let's look at our first term. We have e to the sine theta. I claim that's the same as e to the u. What else do we need to write in terms of u? Well, we still have a cosine theta d theta. Do we see a cosine of theta d theta anywhere? We sure do, and that just so happens to be equivalent to du. Now, I think you would agree that this looks like a much more manageable antiderivative to take. Okay, what's the antiderivative of e to the u? It's e to the u plus c. And then our last step is to be polite. In other words, if our original problem was written in terms of theta, we should really give our final answer in terms of theta. So, what is u in terms of theta? It's the sine of theta. And I think you'll grant me if you take the derivative of this function here, you are going to get what we started with. Remember your chain rule. It's e raised to that power times the derivative of that power. Okay? All right, let's do another example. What if, now not everything matches this perfectly, but the one thing I do want to emphasize here is when you use this technique and you're rewriting in terms of another variable, you can only have one variable here. You can't have u's and thetas, all right? That's a really important thing to keep in mind. So what if I have this? Okay? What if I want to take the antiderivative of this function? Now, a lot of people are like, oh, we can distribute the x squared. No, 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 no. When things are under a radical, they're out of bounds. Okay? So, what would we substitute here? Well, let's substitute what's underneath our radical. We have x cubed plus 1. Okay? So, my next step after I make my substitution is to take the derivative of both sides. So here you get du, and the derivative of x cubed plus 1 is 3x squared dx. Okay? Now, after you do this step, what we want to do is rewrite our integral in terms of u's. Okay? So, what I'm going to first do is say that this is x cubed plus 1 to the 1/2, and then I have, oopsie, an x squared dx. Okay, I just rewrote the order. That's all fine. Okay, well, we know that x cubed plus 1 is equivalent to u to the 1/2. Now, what else in here do I need to rewrite in terms of u? I still have an x squared dx. Do you see an x squared dx anywhere? Yes, but the problem is we got this silly 3. But I claim we can certainly divide both sides by 3 and say that then 1/3 du is x squared dx. So in place of x squared dx, I'll write 1/3 du. Now I'll rewrite this because I just really enjoy having my constants out in front. The antiderivative here is 1/3. When you add 1 to your exponent, you get u to the 3/2 over 3/2 plus a constant. And again, when you divide by a fraction, you multiply by the reciprocal. So I claim we're going to have 2/9 u to the 3/2 plus a constant. And then our last step is to be quote unquote polite. Our question was given in terms of x, therefore we should answer this in terms of x. So we're going to have 2/9. Well, what is u? U is x cubed plus 1 to the 3/2 plus c. And I urge you, take the derivative of this. You're going to need to use your chain rule, and I claim you're going to get exactly what we had inside here. Okay? So let's go through some more examples. What if I have, how about x e to the, let me do this. How about 12x e to the 3x squared dx. All right. Again, what we're going to do is substitute our exponent. We're going to let u be equal to 3x squared. Our next step is to take the derivative. So we get du is 6x dx. Okay? Now what we want to do is we want to rewrite this integral in terms of u. I think you'll grant me that this term becomes e to the u. And now, what else do we still have to write in terms of u? Well, we have a 12x dx. We don't quite have a 12x dx here. We have a 6x dx. But we're going to do a similar thing that we did over there. Would you all grant me that 2 times du would give me 12x dx? Sure does. So we say times 2 du. Pretty cool, huh? So my antiderivative is 2e to the u plus c. And last but not least, we substitute back in using the variable that we started with. All right, what if I have this? What if I want to do the natural log of x squared over x dx? Okay, now you don't have to rewrite this way, but I'm going to, so that when we resubstitute things in, you'll see how it goes back in neatly, okay? All I did is separate this fraction into the numerator and denominator. Okay, so again, what we'll do is we'll substitute what's in parentheses, which is the natural log. We'll take the derivative with respect to both sides, and the derivative of log x is 1 over x dx. And this is sweet. All right, so what do we have? If we're going to write this in terms of u, this becomes u squared. And we still have a 1 over x dx that we need to account for, but that's precisely du. Isn't that fun? So now we take the antiderivative. We get u cubed over 3 plus a constant. And now we substitute what u stood for to answer our question. All right, what if I want to compute this antiderivative? What if I have e to the x plus x in the denominator and e to the x plus 1 in my numerator? Now again, you don't have to rewrite this way, but I'm going to just for clarity purposes, okay? What I'm going to do is I'm going to rewrite this as 1 over e to the x plus x, and that's times e to the x plus 1 dx. I just slid my numerator off, okay? So, yes, there's something in parentheses, but when we go back and substitute here, let's ask ourselves what we would do, okay? There's nothing under a radical. I mean, yes, you can substitute u equals x, but that's not going to get you anywhere, okay? So there's nothing in parentheses. There's no exponent worth substituting. There's nothing under a radical. Well, remember, when all else fails, substitute your denominator. Okay, check this out. Take the derivative of both sides. So du, well, the derivative of e to the x is e to the x. The derivative of x is 1, and that's dx. Okay, so let's now substitute. Do you agree? This becomes 1 over u. Do we have an e to the x plus 1 dx anywhere? We sure do. That's du. Next, take the antiderivative. What's the antiderivative of 1 over u du? It's the natural log of u plus c. Cool, huh? So we can finally write that as the natural log of the absolute value of e to the x plus a constant. Okay, now what if I wanted to do this guy? What if I wanted to compute my integral here? How about we want to compute this? 1 over the square root of x plus 1 dx. And let's evaluate that from 0 to 3. You might ask, how do we involve our definite integrals here? What I'm going to tell you is you're going to do everything exactly the same. You're going to go through, do the substitution, take your antiderivative, rewrite it back in terms of your original variable, and then take care of evaluating. Okay? So in this case, what I would do is I would substitute u to be equal to x plus 1. Then du is equal to 1 dx. Okay? So, well, don't we have 1 over the square root of u? And then in place of dx, we write du. So what we need to do now is write that as u to the negative 1/2 du. Let's take our antiderivative. Okay, if I take my antiderivative, I add 1 to this, I get u to the 1/2 over 1/2, which is equal to 2 times the square root of u, which is equal to 2 times the square root of x plus 1. Notice I didn't put a plus c because I knew once I rewrote it in terms of x that now I'm going to evaluate that from 0 to 3. So we take f of 3 minus f of 0. So that's 2 times the square root of 3 plus 1 minus 2 times the square root of 0 plus 1. Celebrate nice numbers. That's 2 root 4 minus 2 root 1. So what do you get here? You get 4 minus 2, or 2. Isn't that cool? Okay, so when you're doing a definite integral with substitution, you proceed in the same way and then you substitute in at the end. All right, so why don't we do one more example and let us compute this. What if I want to do, how about, they're all so cute. How about, oh, this is a nice, first off, it would help if I was paying attention where I was writing. What if I want to do sine to the 6th of theta times the cosine of theta d theta? Okay? Now, it might seem unclear here what you would substitute, but let me first rewrite this. That's sine of theta to the 6th times the cosine of theta d theta. Now what would we substitute? Again, what's in parentheses? U is equal to the sine of theta. Take the derivative, both sides. And now what we'll do is we'll rewrite. Okay? What do we get when we rewrite this in terms of u? Well, the sine of theta becomes u to the 6th. And again, the cosine of theta d theta is du. Pretty cool, huh? Okay? Take the antiderivative, we get u to the 7th over 7. Notice I'm putting plus c because this is an indefinite integral. And last but not least, we rewrite this in terms of our original variable. Okay? I know these things take a lot of practice. I totally know that, and the best way to gain familiarity is just do as many problems as you have time for. Thank you.